Bionic WheelBot. The Bionic WheelBot is a running robot that can also roll like the cartwheeling spider. The spider, Sabrenus Reichenbergi, can move efficiently in the desert by using both running and rolling modes. The Bionic WheelBot has been developed by Professor Ingo Reichenberg of Berlin Technical University and the Bionics team. To switch from running to rolling mode, the Bionic WheelBot forms two sets of 3 legs on each side of its body into a wheel. 2 legs that were previously folded in during running now extend and push the robot off the ground, propelling it while rolling. This rolling mode allows the robot to move much faster than when running, and it can even handle gradients of up to 5%. Bionic Kangaroo. The Bionic Kangaroo is a robotic kangaroo developed by the Bionic Learning Network. It mimics the unique jumping motion of a kangaroo and can even regain energy during jumps, store it in its artificial Achilles tendon, and use it efficiently in the next jump. The robot achieves its high jumping power using pneumatics and electric motors. The Bionic Kangaroo is equipped with condition monitoring and precise control and regulation technology to ensure stable and dynamic jumping behavior. It can be operated easily using gesture control, where a corresponding hand signal can make it rotate about its own axis. The robot's mobile energy supply is also a significant feature, and 2 different concepts were developed for it, one with an integrated compressor and the other with a mobile high-pressure accumulator. The locomotor system of the Bionic Kangaroo is made of laser-sintered components reinforced with carbon, resulting in a weight of just under 7 kilograms. It can jump up to 40 centimeters high and 80 centimeters in length. Smartbird. The Smartbird is an innovative ornithopter that mimics the flight of a herring gull using active torsion of its flapping wings. The lightweight construction of the Smartbird, made of carbon fiber, glass fiber, and polyurethane foam, and its intelligent onboard electronics make it possible to achieve the unique flight characteristics of this artificial bird. The Smartbird achieves an aerodynamic efficiency of over 80% through its special wing profile and targeted twisting of its wings, providing both lift and propulsion. The Smartbird continuously records data during flight, such as wing position, wing torsion, and battery status, which is checked in real time by software to adjust and optimize the control parameters to new situations within fractions of a second. This permanent diagnosis ensures flight stability and operational safety. E-motion butterflies. The E-motion butterflies are a fascinating project developed by the Bionic Learning Network that combines the ultralight design of artificial insects with coordinated, collective flight behavior. These bionic butterflies are equipped with highly integrated onboard electronics that can control the wings precisely and individually, allowing them to implement fast movements and achieve a lifelike flight behavior. To achieve coordinated flying, 10 cameras installed in the room record the butterflies via 2 infrared markers on their wings. The cameras transmit the position data to a central master computer, which coordinates the butterflies from the outside. This intelligent networking creates a control and monitoring system that could be used in the networked factory of the future. The E-motion butterflies are also highly integrated research test beds with minimal material usage, demonstrating the Bionic Learning Network's focus on miniaturization, lightweight construction, and functional integration. Bionic Ants. The Bionic Ants are a remarkable example of bionic technology that is inspired by the cooperative behavior of real ants. The robots communicate with each other and coordinate their actions using complex control algorithms, demonstrating how individual components can work together as a networked overall system to achieve a common goal. The robots have intelligent subsystems that allow them to adjust flexibly to different production scenarios and execute orders assigned at the master controller level, providing valuable insights for the factory of the future. The Bionic Ants are manufactured using state-of-the-art technologies such as laser sintering and 3D MID processing, which allow the robots to perform both constructive and electrical functions. The actuator technology of the legs uses piezo technology, which offers precise control, low energy consumption, and little installation space. The design of the Bionic Ants is not only aesthetically pleasing but also functional, allowing them to perform tasks efficiently. The robots have many potential applications in areas such as automation and industrial production, and are an excellent example of how technology can learn from nature and apply its principles to solve complex problems in new and innovative ways. Aircuda. The Aircuda is an interesting bionic floating object that is designed to mimic the construction, design, and kinematics of fish fins. It is pneumatically driven and has 4 fluidic muscles that enable it to move in an S-shaped manner and steer smoothly. The Aircuda's tail fin uses the fin ray effect principle, which allows it to develop full power and speed when lateral pressure is applied. Additionally, the Aircuda can balance itself in water with the aid of an air bubble, just like its biological role model. It has a cavity that can be filled with water or air, and a pressure sensor determines the depth and activates the electronics to open corresponding valves and supply the chamber with vacuum or compressed air. All electronic and pneumatic components of the Aircuda are housed waterproof inside the head, and the structure is clad with a silicone skin. The Bionic Finwave. The Bionic Finwave is an underwater robot that uses undulating fin movements, similar to those of natural role models like the turbolaria, cuttlefish, and African knifefish, to maneuver through water. The robot has 2 silicone fins that are completely flexible and do not require any support elements. These fins can generate different wave patterns, enabling the robot to move slowly and precisely while creating fewer eddies in the water than a conventional propeller drive. The fins are attached to 9 small lever arms and are driven by 2 servo motors located in the body of the robot. A third servo motor controls the bending of the body, enabling it to swim up and down. The crankshafts that transmit the force to the levers are correspondingly flexible and can bend due to the presence of a cardan joint between each lever segment. The robot's control and regulation technology is watertight, and its components are matched to one another and safely installed in the tightest of spaces. The robot is also equipped with sensors that measure the distances from the walls and the depth position in the water, thus avoiding collisions with the pipe system. Bionic Opter. The Bionic Opter is an artificial dragonfly designed and created by the Bionic Learning Network, inspired by the flight characteristics of the dragonfly. The lightweight construction and functional integration of components make it possible to achieve the complex flight maneuvers of the natural dragonfly. The Bionic Opter is capable of maneuvering in all directions, hovering on the spot, and sailing without flapping its wings. This unique flight behavior is made possible by the integration of sensors, actuators, mechanics, control and regulation technology, and a powerful ARM microcontroller on board in a compact design. The wingspan of the artificial dragonfly is 63 centimeters, with a body length of 44 centimeters and a weight of only 175 grams. The wings of the Bionic Opter are constructed of a carbon fiber frame covered with a thin foil, while the battery, 9 servo motors, sensors, and radio modules are integrated into the ribcage. The structure is made of elastic polyamide and terpolymer, making the system flexible, ultralight, and robust. Bionic Flying Fox. The Bionic Flying Fox is an ultralight flying object that mimics the flight characteristics of the flying fox, a mammal that can actively fly. Its wingspan is 228 centimeters and body length is 87 centimeters, and it weighs only 580 grams. The Bionic Flying Fox has a wafer-thin, ultralight, and robust patagium that consists of 2 airtight films and an elastane knit, which are welded together at approximately 45,000 points. The flying object uses an external motion tracking system that communicates with its onboard electronics, allowing it to move semi-autonomously within a defined airspace. The Bionic Flying Fox has pre-programmed paths on a central host computer that determine its flight path during maneuvers, and it calculates the necessary wing movements to follow the desired trajectory optimally. The machine learning algorithms allow the Flying Fox to optimize its behavior during flights and fly more precisely along the specified trajectories from lap to lap. Control is effected via the movement of the legs and the thus changeable wing area. The Flying Fox has 2 infrared cameras sitting on a pan-tilt unit that allows them to follow its entire flight from the ground, and the cameras recognize the Flying Fox by means of 4 active infrared markers which are attached to the legs and the wingtips. The Bionic Flying Fox is an excellent example of how biomimicry can inspire the development of advanced technology. Bionic Swift. The Bionic Swift is a group of robotic birds designed by Festo to perform safe aerial acrobatics in a coordinated pattern. These robotic birds are modeled after their biological counterparts and weigh just 42 grams, with a body length of 44.5 centimeters and a wingspan of 68 centimeters. The focus when designing the robots was on the use of lightweight structures, with the goal of reducing energy consumption. The wings are made of an ultralight, flexible foam and are connected to a carbon quill, just like real bird feathers. The individual segments overlap each other like the shingles on a roof, and during the upstroke, they fan out, allowing air to flow through the wing, reducing the amount of power required to propel the wing upwards. During the downstroke, the segments close, allowing the robot bird to fly more powerfully. The bird's body acts as a housing for a brushless motor, 2 servo motors, the battery, the gear unit, and various circuit boards for radio, control, and localization, all integrated into an extremely compact space. The motors and the mechanical system work together to precisely adjust the frequency of the flapping of the wings and the lifting angle for various maneuvers. The coordination of flight maneuvers is achieved through radio-based indoor GPS technology, using ultra-wideband technology. This allows the Bionic Swifts to fly safely and autonomously in a defined airspace.